Hello everybody, how's it going? My name is Leo, aka Knockdeaf, and today we're going to go over a little bit of how 3D models are rendered, what sort of information they have that are useful for technical artists, and so on and so forth. So this is part of a little bit of a series where I teach the basics of shaders for technical art. So if you guys are interested, there will be a playlist and all of the links and such will be in the description. All right, so let's go. We have Blender open here. And the first thing I want to talk about 3D models is that I'm not going to teach you guys necessarily how to make a 3D model. What I'm going to go over is the information that 3D models can store that a technical artist needs to be able to understand. Why do you need to know how a 3D model works? Because very routinely, your shader is going to interface directly with the 3D model. So let's go. So the first thing we need to understand here, it might seem rather basic for those of you who are used to 3D modeling, is what is a polygon? What is a face? What is a vertice? So yeah, so here we have our 3D space here in Blender. So let's create a plane here. And you guys are going to quickly realize that this plane has 4 edges, right? Like, you know, it has 4 sides. It has, you know, like it's a sheet of paper essentially. So you could puncture it if you had, you know, if you go through your finger like this, and what you would be puncturing we call the face. So let me show you guys this in a second here. So let's get the grease pencil here. So this little thing right here is called an edge. Right? This is the edge of the model. This part right here is called the face of the model. And those little dots, you guys can see those little dots in there, they're called the vertices. So what's going to happen is, let me rotate here a little bit. And also, I wish there was an easier way to kill the notes, but there isn't. Anyways, so now what we can abstract here is that if I removed this little vert here, what would happen is that this line would have nowhere to connect. Neither could this one. So they would just disappear. If they disappear, the face will also disappear. So, because they need to be connected. So let's do exactly that. So let's get these vertices and let's delete it. And now we no longer have a face. But if you pay attention, you're going to see that we still have this vert, this vert, this vert, and we still have one edge and another edge. So what we could do here to restore our face is to create another edge along here, and we would have a face. So what is important to note here, what is the lesson here, is that this is the minimal amount of vertices that you need to have a face, right? This is the minimum. You need to have at least 3. You need to have at least a triangle. Because if we delete one of these guys, if I delete this little buddy here, there's no way we can make a face out of it. We can only have an edge. We can't have a face. So this is the first, like, lesson number 1 in 3D is this. You need 3 vertices to make a face. So for that reason, since for us to render our images, we need faces. The faces are the most important actors in 3D, arguably. So since the triangles is the most efficient way to make a face, after all, you only need 3 of them, this is why in real-time rendering, since we're always going for efficiency, 99.9% of the time, we're going to triangulate our faces. Meaning that if we have a quad that is not a triangle, if we have a face that is not triangulated like this, that is not composed out of 3 verts, we're probably going to try to find a way to turn it into a triangle, right? So this is lesson number 1. All right, cool. Now, let's talk about normals, right? So here's the thing. When light hits this face, so let's do a little bit of an abstraction here. So here we have the sun, right? A very 3-year-old drawing of the sun. Let's put a smiley face on the sun. So the sun is going to be hitting lighting information in this face, right? And what is going to happen is that this face is going to reflect some of that lighting. So this is how, PBR rendering works. And the way it judges the direction of the reflection is by usage of the normal. So, well, this face right here has the normal towards, the default normal is going to be the direction, the forward direction of the face. So the face is like here, it's looking up, so the arrow is going to go up. So imagine the normal direction as a little arrow that goes from the middle of a face straight up, right? Straight forward, actually. But yeah. So now let's get this face and let's rotate it. Guess what happened now? Now, if we assume that this side of the face is our the forward-facing face. I know, sounds weird, but that's how it's called. Then the arrow, the normal direction, has also shifted along with the rotation. Now, you can manipulate this with normal maps, but this is a talk for a later day. For now, this is what we need to know, right? So in a shader, a common thing for us to do would be, for example, we could try to move this face, right? We could try to move the face along its normal direction, meaning we would be moving it towards this direction here, right? So this is an example of real-world usage of this feature of a 3D model, right? All right, cool. So now let's talk about UVs. So let's make a cube here, right? So if we're going to the UV editing mode, you guys are going to notice that we have this 2D abstraction of our 3D model. So if I select, let's do like this. If I select this face right here, this is the middle of the cube on the UV abstraction. So the one directly by its side is this one. If we select this one, it's this one, right? Part of the cross. Imagine it as an origami, right? And then it becomes really easy to understand. So, by the way, a quick fun thing, the reason why it's called UV, it's because it comes right before the XYZ coordinates. So since we use the XYZ to represent the 3D coordinates, the 2D coordinates are the UV, right? It's a little bit of a fun thing. So we're going to talk more about UVs today, but the important thing here to take away is that the UV is a 2D abstraction of the positions of the polygon, of the faces, right? And the vertices and the edges. So we have the edges, as I showed before, we have those edges and, oops, come on. We have the edges, we have the vertices, and we have the faces, the same way that here on the UV land, we also have their representation on a plane, on a 2D plane, right? So it's an abstraction that tries to match one to one and marry one to one another. All right, cool. Now, before we jump into more details about the UV, I just want to quickly cover other stuff that we have here on a 3D model that we can manipulate. We have Vertex Color. So we know what a vert is. This is a vert. It's this little dot right here, right? All right, cool. So now we know that this is a vertice. This is a vert. So what is a color? Well, we can assign a color to it. So allow me to demonstrate. Let's make a little bit of an annotation here, right? So let's say that this little buddy here is going to be red, right? And that this little buddy over here is going to be blue, right? Oops, blue, cool. So let's go here into Photoshop. And let's do a little bit of an experiment, shall we? Let me get here a fully white plane. And let's get our gradient tool. And let's say that part of the gradient is going to be fully blue, and the other part of the gradient, come on, bro. All right, and the other part of the gradient is going to be fully red, right? And now, if I were to draw this gradient like so, this is the result we would get, right? We would get very, very red here that shifts, goes into the mid purples, and then goes into the blue. All right, so what is happening here is an interpolation. It is taking the numbers from the arrays that we have learned in the previous video, and it is linearly interpolating them. So what is interpolation? Interpolation means that it's gradually shifting from the value. Hold on one second. Let me get like a yellow here. It is going from value A to value B at a constant rate, which means that at 0.5, it has 50% of B and 50% of A, which is purple in this case, right? So this is linear interpolation. You can interpolate non-linearly, but you know, that's a talk for another day. So this is what is going to happen here. This is value A, this is value B. So let me show you guys. So if we go here into vertex paint mode, and we grab this vert right here, we can now make it fully red. I don't know how I'm gonna get the full red here. Wait, let me go RGB. Okay. So let's paint this vert fully red. And now let me go into fully blue and paint this vert. Come on. Come on. Hold on. Ah! No. Here we go. Selection tool. Vertex paint, and paint this vert fully blue. And now look at what we have here. We have the same thing that we have on Photoshop. The very tippity tip is fully red, the very tippity tip on the opposite side is blue, and in the middle we have the purples. So this is how Vertex Color works. For each one of those little vertex points, so this one, this one, this one, this one, if you had more verts, we would have more options. We can paint a color, and one is going to linearly interpolate onto the other, right? And this information is interesting because you can use it to put color into your 3D models, although that is not very common. You can do it. You can also use it to mask things, right? To do mathematical operations. If anything multiplied by 0 is 0, and 0 is transparency in most shaders, then you can say that, oh, I don't know, this is going to be 0, this is going to be 0, and now all of a sudden, this model is going to be slightly transparent on those sides here, right? This is an example of that information that can be used. But you can use it to overwrite your normal information. You can make something like the Fortnite apparition shader. You can coordinate the order that things move in, snap in into an animation. And you can do a lot of things with this information. Cool. So that is Vertex Color. Now, not only that, but verts, they have a bunch of information. Another information that they have is translational information, meaning they have coordinates. They have, like, each one of these can save their position, scale, rotation, and I think that's it. So, yeah, and all of those three things here, this is a vector 3. So it's a vector of 3 numbers. This is a vector 3, 2. This thing here is a quaternion, but essentially is a vector 3-2. Well, in Unity's case anyways, it's a quaternion. So this means that you have actual information on those verts that you can save, and you can do a lot of trickeries with this. So you can move those verts using shader, you can scale them using shader, you can rotate them using shader, you can do a lot of stuff using shader, because since they have this information, you can manipulate those informations using shaders. And we will do some stuff, by the way, like this in the future. We will most definitely do some experiments with this. So also, when it comes to rigging, so rigging is like things that have bones and move. So when it comes to rigging, when your model is created, it first like, this is a static 3D model, right? But you can put weights on the weight paint, and you can essentially say, oh, this vert right here has a lot of weight to that bone, and this vertex, essentially what's going to happen is that you're going to be telling the 3D model that, you know, this is going to move along when that bone moves along. So this is another information that can be manipulated through shaders. All right, so this is like the basics of a 3D model, but let's talk a little bit more about UV though, because now it's the first time that we're gonna actually talk and do a little bit of shaders, right? So let's go. So what are UVs most used for? So the two biggest usages of the UV node inside of Shader Graph is going to be the following. You're going to do texture sampling, and you're going to do gradients. So, all right, let's go over here and let's drag this out and let's do a split. And what you guys are going to quickly realize as soon as I finish doing this, 1 and 1, you guys are going to notice that a UV is two gradients that goes from black to white in two directions. One goes from black to white horizontally, and the other one goes from black to white vertically. So this is a mathematical abstraction. Allow me to show you guys what I mean. Imagine you have a texture. Hold on. Imagine you have a texture, a square texture, fully square texture, okay, that is 1024 by 1024, right? So you have this texture here, and you want this texture to be overlaid on a cube 3D model, okay? This is the shittiest cube I've ever made, but yeah. So what we can do here is very simple, right? We can say that for each face of our cube, right, we can just overlay this texture on the face of the cube. So easy peasy, right? But now let's suppose that for performance reasons, your game is running too slow, and the artist has decided to cull this texture and to use a 512 texture instead, so half the resolution. And the code that you had previously written for your cube overlay was very simple. You did the following mathematical abstraction. You said, takes this vert, right? So you have a cube, right? So let me kill this cube here. So you have a cube, right? So the abstraction that you did was the following. You said this is going to be pixel number 0. This is going to be pixel number 1024, right? And then you're going to go to our texture that's 1024 by 1024, and you're going to go to pixel number 1 and overlay pixel number 1 here. Pixel number 2, overlay pixel number 2. Pixel number 3, pixel number 3, right? And you're going to do that on the horizontal axis, horizontal, and you're going to do that on the vertical axis. So this is going to be pixel number 0. So this is going to be the vertical axis. The vertical axis, right? So this is the way your code is written. It is going to scan the texture and overlay the pixels on that manner. So guess what? Now you're fucked. Because now your texture is 512, which means that there's not enough pixels on your texture for your code to go from pixel number 0 to pixel 1024. So you say to yourself, all right, cool, no problem. I am going to do an abstraction. Instead of reading my texture on 512 pixels, instead of using an absolute number, no, I'm going to be smart. Observe. Hold on. Observe what you decided to do. Now, instead of reading your texture on its absolute pixel size, you decided to say the following. This edge of my texture is equal to 0. This edge is equal to 1. And the same thing here. You decided to say this vert is equal to 0. This vert is equal to 1. Sorry guys, I had to pause a little bit. My mom was asking me to make coffee. So this one is 0, this one is 1, right? The same way that we're abstracting the same way that we're abstracting the texture. This one is 0, this one is 1, right? Cool. So now what you're going to do is that you're going to scan the pixels and say that, well, this pixel right here is in 0.1% of my gradient. So I'm going to place it at the equivalent position, 0.1 position. So this is how UVs work. It's a very smart abstraction, and without this abstraction, it would be virtually impossible to have textures variations in a 3D rendering engine. So this is a really smart abstraction that people did back in the day so that they can draw their textures. So you need to think of this kind of like percentages, right? You're overlaying your texture on the face of your model based on percentages. So think of it as 0% to 100%. And some of your textures are going to be at 50% or 78%, right? Things like that. So this is how UV is abstracted. So what this means is that a good way of thinking about this UV here is thinking not only on percentages, but thinking on things like, well, let's say that what would happen if I added 0.1 to my UV. Now, as you guys can see here, the bottom 0.1 doesn't exist anymore, right? This bottom black here doesn't exist anymore. So if I were to overlay a texture over there, the texture would be cut on the first 0.1 percentages. So if I had a texture and overlaid on a 3D model, it would be the same as me cropping the texture right here. And all of this part right here would be lost because I added 0.1%. I could do the opposite by, adding negative 0.1%. Then I would extend this first portion here. All right, cool. So let's do a little bit of a proof of concept here. Let's literally take our UV and let us just slap it into the color, right? And let's see here how our scene looks. You guys can see now that our plane has the UV coordinates because the UV coordinates haven't been messed with. Now let's do a little bit of a texture sampling, right? Let's use this for texture sampling. So let me get, one second, a texture here for us to work with. I have a really good texture for this. I should have prepared this before. So let's get this texture right here, right? So now if we put this here and we plug our UV in, now what's going to happen is that we're going to overlay our texture like so, right? Like the texture is going to be default overlaid. All right, cool. Nothing new there. But guess what? Let's say that we want to show this texture twice, right? Well, guess what? If we multiply our UV, and remember, it's two gradients. So each gradient is stored on a different channel, like I explained on the first class. So this means that if we take a vector 2, it is going to be equivalent to those channels. So the x is going to multiply the equivalent x channel on the UV channel, and the y, the equivalent y channel on the UV channel. So if I multiply here, now we're multiplying one vector 2 of gradients by another vector 2. So what we can do here is, for instance, if we multiply this by 1, it's going to be itself. So the texture is not going to be changed. But if I put 2 in here, look at that. Now we have two gradients along the horizontal axis, which means that now the texture is going to repeat itself 2 times along the horizontal axis. Let's save this and test it out. And blammo, look at this. The texture is repeating twice along the horizontal axis. Because as I said before, those are numbers. You can multiply them, which means that you can also divide them. You can also do anything, right? So yeah, you can do anything. So let's divide. Let's divide. So now if we divide these, you guys are going to notice, oh, this is funky. Oh, because it's a gradient, sorry. Yeah, it's not going to work because it's a gradient. It does yield a very funky result though. It is funky. Let's be real here. So this happens because you're dividing a gradient. It's not absolute values. But you can also multiply by divisions, right? So for instance, this is 1 tiling once on both axes, right? So what is 1 divided by 2? Well, it's 0.5. So we can just do this and it's going to work, right? So you can't divide a gradient, but you can multiply a gradient by the result of its division, if that makes sense, right? All right, cool. So this means that you can manipulate things. But guess what? This is not the only thing that UVs are used for. Because remember what I said before? These things, they're gradients. Look at this. They're gradients, guys. They are gradients. Let me get a mask, channel mask. Look at this. Look at this. If I get only the green channel, guess what? It's going to be a vertical gradient. So if I put my texture in here, right? And let's go into our graph settings and let's make it transparent, right? And I plug this gradient into our alpha channel. Actually, let me do a split. Let me just put this here. If I put this into an alpha channel and I save it, look at this. Now we have transparency from that gradient. But, as I said before, not only these are gradients, but they are also numerical gradients, right? Which means that you can do a lot of stuff with them. So let's do another proof of concept. So let's split the R channel and let's multiply only the R channel by 12 or something like that, right? And now let's do a fraction node. And now you guys are going to see that we have those stripes here. Now let's do a step. And let's see here which bias is going to look good. And let's go for 0.26. So it only shows the 0.32, doesn't matter. Let's put it into the alpha. Blamo, blimo, blamo. Look at that. We have ourselves a stripe alpha channel. Why is that? Well, essentially, since those are gradients, when we multiply them and when we fraction them, because if you like, you can do anything to these that a number can. I don't know if I'm explaining myself properly. So any mathematical operation that you can think of, you can apply to them, and you're going to yield a texture result that you can plug to a rendering pipeline. So another great example of this is circular gradation, right? So let me show you guys here. So we have a distance node. So the distance node returns the distance from a point that you specify. So since those are gradients, let's do a little bit of a thingy here. Let me show you guys this really quick. Since these are gradients, and as I said before, and I'm going to repeat this once again, I'm going to repeat it once again, guys. 0 to 1, 0 to 1, cool, right? So now this means that we have a middle point, right? So the middle point here, this is 0.5, and a middle point here, this is 0.5, right? So if we trace this middle point with little dots, this means that the coordinates for this point right here is 0.5, 0.5, 0.5, right? This is our middle point. All right, cool. So this means that if I want the distance between those absolute values of our gradients and 0.5, 0.5, which is the very middle, we're going to have a gradient that goes from here, 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 and here to here. So we're going to have a radial gradient, right? This is like, I know, actual mathematics, right? But it's useful, actually, you know. I also didn't want to believe it. So let's create a vector 2. I was terrible at math in high school, so I kind of hate this, but you know, it is what it is. So let's 0.5, 0.5, and look at that. We have a radial gradient. Now let's plug this radial gradient in here. And now we're going to sample our texture from the middle outwards. Looks very funky, doesn't it? Or we can also use it to do more operations. Remember what we did before, guys? That we multiplied and then we stepped, and then we multiplied, fractioned, and stepped. Guess what? We can do that again. Let's multiply. Let's use 5. I don't know. Let's fraction it up so that we get multiple gradients once again. And let's step. And let's change here our bias. All right, cool. Now we can put this here. Let's remove this UV. And look at that. Now we have a target practice looking thing, right? Very cool. So all of this is by using the power of gradients. But guess what? What if I can tell you that we have another powerful tool in our tool belt? So let's grab the time node. What is the time node? So the time node, for now we're only going to cover time. Later on we're going to cover sine time, cosine, delta, all of that shit. For now, just time. Time node is a float that just increases over time. That's all it does. So let's add the time node to our UV. Now let's slap it over here. So now what's going to happen is that as time passes along, we're going to forever increase the starting point of our gradients, which means that forever we're going to make it move along, right? So now if we keep all of the operations that come after it, now we have a stripe that moves along horizontally, right? The reason why it's horizontally, it's because we're adding it to the x and the y. But we could make it one axis only, right? So how do we do that? Well, we can split. We can get only the red channel and add it, right? Then we can add back our green channel. No, sorry, we're not going to add. We're going to append, combine, sorry. So this is our red channel. This is our green channel. And now if we slap this over here, now it's no longer moving horizontally. Now it's moving only, it's no longer moving horizontally. I forgot the name. Horizontal? Vertical? What is the name of the inclination? Well, I forgot about it. Anyway, the point is now it's moving horizontally, right? So yeah, those are the basics of UV manipulation. This is a lot of information, guys. I know, okay, it's very hard to grasp, but I think that we're gonna have, along this class, a bunch of aha moments, you know, those little moments where you're gonna go, oh, now I get it, right? Hopefully those visualizations that I did were enough to show you and give you some of those aha moments, right? Hopefully. So yeah, but don't worry if you didn't understood everything straight away. We're going to use a lot of UVs throughout the series, and you're going to have lots and lots of opportunities to grasp the concepts. I also jumped the gun a little bit, and I think I, showed some mathematical things like the distance node, for example, and the distance concept. It might be a bit daunting at the start, but trust me, over time, this is going to become second nature almost. And those mathematical concepts like this visualization is very good, to visualize, I think, because it gives you an extra level of understanding very early on that is going to save you a lot of headaches. So yeah, if you didn't understood everything right at the start, don't worry. Leave your questions down below. I'm gonna answer all of them. So thank you so much for watching. And in the next video, we're gonna know a lot about we're gonna learn a lot about other nodes. So we're going to cover the basics of subtraction, addition, multiplication, division, things like that. So thank you so much for watching. Goodbye.